Starting. Okay. So hello everyone. Welcome back to our sessions on machine learning. So, it's been like 2 weeks since we had a last session, but still I hope at least you remember some of the points that we had discussed in our last session. So can somebody just summarize briefly the important points that were discussed in our last session? What was the primary discussion based on? Can somebody please speak up?
We looked at a multiple regression. So with more than one independent variable. And and then we looked at how we can use gradient descent to find the weights. Yeah.
Right. Thanks, Rafael. So we looked at not just on gradient descent, we also looked at normal equations, right? We actually discussed about two different techniques, right? So basically, we discussed about multiple regression, and then when we looked in detail about what is the general idea behind gradient descent, and then we looked at the specific case of multiple regression, and we also saw how we could use normal equation. Normal equation means what we did there was we found the derivative, right? Partial derivative to be exact. So we found a partial derivative of the loss function with respect to the W vector, right? So, okay, sorry. So partial derivative was in the context of gradient descent. So in the case of normal equation, what we did was we found the minima of the function directly, right? So we found the point of minima by taking the derivative, equating it to 0, and then we got one equation, right? W equal to x transpose x inverse x y, something of this form, right? And then we saw what was the difficulty or what are some of the problems that could crop up when we use the normal equation. Then we looked at gradient descent, which is an iterative procedure, right? So here we do a lot of iteration, and then we also saw how the partial derivative, right, fit into, or how the partial derivative helped us to move in the direction of the steepest descent, right? So this was basically the important topics or the important points we discussed last class. So today we'll discuss some topics, a couple of important topics. And first we'll revisit what is a polynomial regression. So we know that in polynomial regression, the relationship between the independent variable x and the dependent variable y is modeled as a nth degree polynomial in x. Okay, so we'll first consider the case when we have only one independent variable. So even though we have only one independent variable, we are modeling it as an nth degree polynomial in x. Okay, so that means now, so in a way it looks like a multiple regression, right? So if you look at x as one feature, x square as another feature, x raised to m as another feature, then it pretty much looks like a multiple regression problem, right? But with respect to x, if we are looking at it, we are actually fitting a non-linear hypothesis. Okay, so hypothesis is actually, in machine learning literature, hypothesis is used synonymously with model. So hypothesis actually refers to a model. So when you read some literature, some of the resources, you see this terminology hypothesis. It just refers to model. So I just wanted to introduce this term also because I don't want you to get confused about what a hypothesis is. So this is only related to the machine learning literature. So in statistics, it's a different thing. Okay. So basically, with respect to x, we are fitting a non-linear model, right? But when we do a matrix representation, right? So remember, in the last couple of classes, we have been looking at how to use matrices to represent these set of equations. Given the data, how to come up with the equations and the corresponding matrix representation. So now it looks kind of similar to the multiple linear regression problem, right? So we have these ones corresponding to our intercept term W0. And this X1, right? X1, X2, that is, all these terms actually refer to one feature. Let's call it F1. And the square of these X's could correspond to the second feature. And similarly, let's call it Fn, M features. Right. So that means the estimation problem is still linear. So even though the features are modeled, right? So even though we have the polynomial terms coming in, if we treat them as different features, then it actually reduces to a linear estimation problem, similar to the case of multiple linear regression, right? So now here, as I said, we can consider x square, x cube, etc. as different independent variables. So then what happens is now it becomes a special case of multiple linear regression. And so we can use the same techniques that were used to compute the weights, that is gradient descent as well as the normal equation, right? So that means polynomial regression. So again, just see that here in this case, we just had one feature and then we generated a polynomial based on X. We can also have polynomial regression when we have more than one feature, right? So for example, if we have two features, let's say X1, X2, then the polynomial regression, the polynomial that could be fit can be something like this. So we could have W0 plus W1 X1 plus W2 X2 plus, let's say, W3 X1 square, W4 X2 square plus W5 X1 X2. Okay, so this is a polynomial of degree 2 basically, right? And we have some interaction terms as well. Correct. So similar to that, we can have polynomial regression when there are more than one independent variable, but then still it will, it will actually boil down to a multiple regression problem because the estimation is linear, as we have seen just now. Okay, so we'll see an example here. So we use polynomial regression when the data distribution is more complex than a simple linear model, right? So in many cases, you will see that, okay, the data cannot be represented suitably by just a linear model. So then we could go for a more complicated model. So that is when we can consider these polynomial terms of the features. And then let's see what happens here when we fit a line. So you can see here, right? It does not represent the trend very well, right? But then when we use a polynomial regression of degree 6, then you can see that, okay, then you have captured that, the distribution quite well. So that is where we use polynomial regression. So then, as you have seen, there is nothing new to discuss here. We could use the same weight estimation techniques like gradient descent and normal equation. Okay. So now that we have this polynomial regression, right? So now you will think, right? Okay, now we could actually use polynomials of a very high degree, let's say 25 or something. So then you get a very rich feature space. So you would think, okay, then it would be quite possible for you to represent any data using, such rich feature space, such rich or such higher degree polynomials, right? So then what could be so difficult in that? So that is where we have something called overfitting coming in. What is overfitting? So overfitted model actually performs very well on the training data. That means you could get a training error of 0. But then when you use this model on the test data, then its performance drops significantly. That means you get higher errors. So what happens there is that the model learns the detail and the noise and the training data as concepts. So as we've already seen, the training data also contains noise, right? So an overfitted model not just learns the pattern, but it also learns the noise. So because of that, it will not generalize well to new unseen data points. Okay. So these concepts that are learned based on the detail, based on the pattern as well as the noise, will not fit well for the unseen data. So that is why the model will fail to generalize. Okay, so I'll first show you an example here. So here you can see, right? So the same data set we are using. In the first case, we have used a polynomial regression, right? So it looks nonlinear in terms of x, but if we actually take the polynomial terms and then do the plotting, we'll see that it will be a linear surface. Okay. And in the second case, you can see the line. So which one do you think better represents the the pattern in the data? It should be the line, right? Because if you look at the polynomial, the polynomial regression case, the training error will be very less as compared to the simple linear regression case. But still, when new data points comes, right? So the new data points could be somewhere like here and all. So if you try to extend this function, it will go like this. Whereas with this model, it will try to predict correctly. Right. So that is what is happening. When it tries to reduce the training error, it is actually trying to fit the noise as well, because of which we are getting almost zero training error. So then how can we reduce overfitting? So either we can increase the amount of training data. We can use a lot of training data so that the model does not learn the noise so much. And we can reduce the model complexity. Now, what is model complexity? Model complexity refers to the number of parameters that is, represented as a part of the model. So it could indirectly refer to the number of features. So if we have only limited training examples, and if we are using a lot of features. So for example, let's say we have just 100 observations, and then we are trying to fit a polynomial regression model of, let's say, degree 10 or something, then it will definitely overfit. Why? Because we don't have enough training data so as to learn a good model that has sufficient confidence on its predictions. Okay, so if we are trying to build a complex model, then we should have enough data points to justify that model, right? So just with some limited observations, we should not try with a lot of features. So that is about overfitting. Now we look at another extreme, underfitting. Now what does an underfitted model do? It performs poorly over the test as well as the training data set. Okay, so in case of overfitting, it was like training error was 0, that is superior training performance, whereas the performance in the test data set was very poor. But here the model is performing poorly in the case of both test as well as the training data set. So that means the model does not model the training data, neither does it generalize to new data. Okay, so it is not learning the patterns from the training data at all. So then what can we do to reduce underfitting? We can increase model complexity by adding new features, right? So maybe it could be that, like I said, we don't have enough features. So then we can try adding new features and see if the model is able to perform better. Or else we could try alternate learning algorithms. So as we all have seen, when we choose a model, there is some assumption, right? Assumption on the relationship between the target variable and the independent features. So it could be that, that assumption is wrong, or wrong in the case of that particular data set. So then we could try other learning algorithms or other model and see if we get a better performance there. Okay. So now here you can see all the 3 cases. Right. So for the same data set, when we fit different type of models, you can see how it is coming in. So in the first case, right, this is underfitted. Why? Because if you look at the training error, so all these are training data. Okay. So we don't, the test data is nowhere in picture here, but you can see that even in the training data set, there is a very high error. Right. And then if you look at the other extreme, we have overfitted data. So see what it is learning. So this is some polynomial regression with a high degree. with a high degree polynomial. So now the training error is almost 0. But do you think it will generalize well for unseen data? No. So you will see that when you test it on the test data set, the performance is bound to decrease. Whereas for the good fit, right? So you can see that, okay, the training error is not 0, but it captures the pattern quite well. Okay. So again, I would like to re-emphasize that this is why we always, when provided with a data set, we do a split, right? We have the training data set and the test data set. And the learning algorithm does not see the test data set at all. So it just learns on the training data set. And finally, once the model is there, we evaluate its performance on the test data set. So that will tell us how good the model can generalize. Okay, so that is the significance behind doing the training test split. Okay, so now we look at, okay, so before that, so you can see how the underfitting and overfitting can be explained on the basis of the model complexity as well as the training error. So initially when the model complexity is very low, it's very low means we are using a limited number of features, a couple of features maybe. Then what happens is you can see that the training error as well as the test error will be very high. And as you increase the number of features, then both the training error as well as the test error comes down till this point, after which the training error still continues to decrease, but the test error increases. So this point is actually what gives you the best fit. So this is the underfitting region, right? Why? Because the model is not performing very well on both the training and the test data set. And this regime represents the overfitting region. Why? Again, because the training error is very low, right? But the test error is high. Okay, so now just to get the idea clear, you can relate it to a scenario from your real life. Suppose there are 3 kind of students, okay? So the first student is not at all interested in learning. So his class test score is also poor as well as the final test score is also poor. So that is how an underfit model, kind of behaves. Like it doesn't learn anything at all. It's not interested in learning, something like that. So that is our underfit or biased learning model. And then we have another person. Okay, he memorizes the lessons. So what happens in the class test? So most of the questions, maybe comes from the notes or something. So he does very well. Whereas in the final test, when he is presented with some new conceptual questions or something, there his performance degrades. And then we have the other case, best fit case, where, conceptual learning is happening. So what happens is that, okay, this person learns the concepts well. So in the class test, he might not score as well as this person B. Maybe because, that person has not memorized the lessons and all. But still, because he has actually learned the concepts correctly and knows how to apply it, he performs well in that person performs well in the final test. So that is how the best fit model behaves, right? That is the expected kind of behavior also, right? That you have to perform well, consistently. Okay. So now we look at a few cases where the least square regression model performs poorly. Okay. So one is the case of multicollinearity. So multicollinearity occurs when one or more of the independent variable can be expressed as a linear combination of the other independent variables. So suppose we have 3 features, let's say F1, F2, and F3. And let's say F1 equal to A F2 plus B F3 for some AB, okay, for some AB belonging to R. Okay. So this is when we say that, one feature, that is one independent variable, can be represented as a linear combination of the other independent variables. So then our model, if you remember, is of this form, right? That is W0 plus W1 F1 plus W2 F2 plus W3 F3. But since there is a relation like this, right? So then what happens is that the weights learned is very sensitive to data. I mean, because if you can see, like if we change W2 and W3 slightly, then W1 is also kind of, I mean, it changes, right? So you can find multiple combination of weights for W1, W2, and W3, such that it relates to the minimal minimal loss model. Okay, so I don't know how much you're able to get the idea, but if you look, see, because one feature can be represented as a linear combination of other features, and we have something like this, right? So here we can represent F1 as W1 AF2 plus BF3, right? But in this F3, in another case, can be represented as W3 equal to 1 by B F1 minus A by B F2, something like that. So that means that because there is some dependence between the features, right? So the weights that is learned is kind of very sensitive to the data that is used to learn. Okay. So this causes overfitting. Overfitting, why? Because the coefficients change erratically in response to small changes in data. Okay, so that means if you first take one small subset of the data and train the model, then you will get one set of weight vector, right? And then if you take the other subset of data and then change and then again train the model, you will get another weight vector. But what we want to happen, but what we actually would like to have is that these weight vectors should not be, too fluctuating. I mean, there should not be much difference between the weights, because otherwise the pattern is not represented, or the pattern has not been learned well in that case, right? If there is very high difference between the weight vectors learned on subsets on different subsets of the same data. But if we have multicollinearity, then these coefficients will change erratically in response to small changes in data. So this could cause overfitting. Okay, so that is multicollinearity. And the second case is, okay, when the number of independent variables is larger than the number of observations. So we already discussed that in the case of overfitting, right? So then there also we'll have a problem. So for example, if we have D, that is the number of features greater than N, that is our number of observations. So if we have, let's say 100 features, but only if we have 50 observations, then there is a chance of overfitting. There's a very high chance of overfitting that case. So the third case is when we have outliers. Now, what are outliers? So outliers are basically the data points that differ significantly from other observations. So we'll see a figure here. So now you can see, right, that this point is lying away from all the other points, right? It does not seem to follow the same distribution as the other data points. So then what happens here is, see, if suppose this data point was not there, then do you think this is the best fit line? No, right? We could still come up with a better line. Could be something like this. But just because this point has come up, what happens is that this line, kind of moved, kind of shifted. So that is one problem, right? Just because of one point. So this could be a noise point, right? So ideally, there should not be so much of a difference in the weights learned by the model just because of the presence of an outlier data point, right? But then because of the loss function, the nature of the loss function, we are using squared loss, right? So because of the nature of the loss function, this model is very susceptible to the presence of outliers. Okay, so we have to be careful when we fit a regression model. We have to see if there are outliers. So we have to maybe first do some pre-processing to either remove the outliers or use some technique to handle them. Otherwise, then there's this problem that we may not get the best possible model. Okay. So now we look at one technique to avoid the problem of overfitting, which is called as regularization. Okay. So regularization actually tries to minimize. Okay. So we always wanted to minimize the sum of the squared error, right? But now regularization will try to minimize the loss function as well as the model complexity. Okay, so model complexity is related to the parameters learned, right? The parameters means the weights. Okay, so model complex. So it will try to reduce the model complexity. How? So it discourages learning a complex model by shrinking the coefficients towards zero. Okay, so we have a weight vector being learned, right? That is what the model is actually being represented, right? So we have the weight vector being learned. Now, what is happening is that it tries to reduce the model complexity by shrinking the coefficients towards zero. Now, how does that help? How does shrinking the coefficients to zero helps in learning a less complex model? So if you remember, right, if we have some, let's say some data points, let's say this. Okay, so the best fit model could look something like this, whereas an overfit model could learn something like this. So we could use a polynomial regression model with some, let's say, with of degree m equal to 10 or let's say 20 or something. Okay, so then here what happens is that we have a very big feature space. And there is a weight vector corresponding to, there's a weight vector with wi's corresponding to each of these, right? So we'll have x1 square, x1 cube, then x1 4, x1, like that till we have x1 raised to 20, right? And then we have the weights, right? So this will be w1, w2, etc., w20 for a single feature. So if we want to avoid such, complicated, curves being fit, if we want to avoid such complicated curves being fit, what could be done is like we can have some of these weight vectors or some of these coefficients is zero, right? So let us suppose that this high curve, right? Okay, so this is like, I'm just stating this for simplicity. Let's say that this curve corresponds to x to the power 15 and this curve corresponds to x to the power, let's say 17 or something like that. So if we can make the coefficient, right? So there is a W15 here. So if we can make W15 very small, let's say 0.01 or something, and let's say x17, if we can make it very small, let's say 0.05 or something, then what happens is that this curve, right? This curve kind of is removed from the picture because the contribution of x to the power 15, right? It's like very less. So we know, right, this coefficient actually signifies the importance of that feature with respect to the target variable, right? So if we can reduce these coefficients, the value of these coefficients, then what happens is that it corresponds to those features being less important in our from modeling our curve. Okay, so that is what is happening here. So that is why we say that by shrinking the coefficients towards zero, we can prevent a complicated model from being learned, right? But then we have to also reduce the squared error, right? So it's like we have to achieve two things. We have to learn a less complex model that performs well on the data. That reduces the squared error. Okay, so that is why in regularization, we have two functions. One is the loss function and the other is the constraint. The constraint is placed on the weight coefficients. Okay. So again, we can add different forms of constraints, and some of the popular ones are ridge regression, lasso, and elastic net. So we'll try to look at a couple of these now. So first we'll see what is ridge regression. Okay, so ridge regression is also called as L2 regularization. Why? We'll see in a moment. So here, the constraint that is added is a linear function of the squared coefficients. Okay, so that means we are adding some constraints on Wi square. Okay, so it is basically limiting the L2 norm of the weights being learned. Now, what is the L2 norm of a vector? So we have a vector V, then its L2 norm is simply what we are doing is we are taking the square of the components of the vector, summing it up and taking the square root. So for example, if our vector is, let's say 2, 1, 3. Okay, so V is 2, 1, 3. Then its L2 norm is basically square root of 4 plus 1 plus 9, which is equal to root of 14. Okay, so here we are actually squaring it, right? So 2 square plus 1 square plus 3 square. So that is why we are saying that it tries to limit the L2 norm of the weights being learned. Okay, so now the loss function for ridge regression is given by, so this is our ordinary least square regression, right? So I mean, this is the loss function for our OLS. And in this is where the regularization term is coming in. So now we have, so we have a new term lambda, and lambda multiplied by the sum of the squares of the weight coefficients, right? So lambda is basically the regularization parameter. So it controls the trade-off between the model complexity and fit to the data, right? So here we have two objectives. So what happens when we try to reduce the weight coefficients? Then the error, the training error, or this part will increase, right? But then we want to balance both, right? So we want to keep the the training error in a minimal fashion while reducing the model complexity. So this lambda parameter tries to control that. So what happens when lambda equal to 0? Then this term vanishes, right? Then we get our ordinary least square regression, right? OLS regression. Now, what happens if lambda is very small? Same thing, right? So when lambda is very small, then again the focus goes to reducing the training error. Why? Because this part is like, see, even if the weight vector is even if the components of the weight vector is very large, we are multiplying it with lambda, right? So that means its importance reduces. Now again, what happens when lambda is greater? I mean, it takes a higher value. When it takes a higher value, what happens is that the focus comes here rather than here, right? So the model tries to learn a less complex model. So then what happens is that the training error is not getting that much of an importance. So then what happens? Underfit happens, right? So we are learning a very low complexity model that does not, that need not perform well on the training data itself. And when lambda is very small or even 0, then what happens is that there is, there is not much focus on the model complexity part. We'll be focusing on the loss function. Then we will have overfitting, right? So lambda is usually greater than 0, because if lambda is 0, then we have the usual ordinary least square regression. And when lambda is small, it leads to overfitting, because again, we are focusing on this part. And when large lambda is used, now the focus will be here, the model complexity. We'll try to learn a very less complicated model, which could perform very poorly on the training data itself. Right. So that is how this lambda is it is controlling, right, where the focus should be. So it is a trade-off between the model complexity and the fit to the data. So ideally, we want to balance both, right? So here you can see an example. So this is the data points. And if we use a polynomial regression of degree 25, then we could get something like this. This could be the curve that is obtained. We use ridge regression on the same polynomial, right, with degree 25. Then here you can see, right, see this part is gone now. Probably because the features, probably because the weights corresponding to, the features contributing to this peak has been reduced, right? And but now maybe you can see that, okay, earlier this point was a perfect fit, but now it is not a perfect fit, but that is okay, right? So definitely this seems to be a better fit than this, right? So that is why ridge regression, by choosing a good lambda value, it can try to learn a less complex model that can fit the training data well. Okay, so that was about ridge regression. Now we look at another case, which is called lasso. So lasso stands for least absolute shrinkage and selection operator. Okay, so it is also known as L1 regularization. Okay, why? Because it penalizes the sum of absolute weights of weight coefficients, or the L1 norm. So earlier we were looking at the L2 norm, right? So we were basically trying to So we were trying to do Wi square. We were trying to minimize this for ridge. But for lasso, what we are doing is we are trying to minimize the absolute value. So if we have our weight vector like -2, 1, 3, let's say, the L1 norm will be mod of -2 plus mod of 1 plus mod of 3, which is equal to 6. Okay. So now the loss function, we have the regularization term where we have this regularization parameter. And here, instead of taking the squares, we are taking the absolute value of the weight vectors. Sorry, the weight coefficients. Okay, so then the question is, what is the difference when we use this absolute value of the weight coefficients as opposed to the squared value of the weight coefficients? There should be some difference, right? Otherwise, why two different techniques? So one thing to note is that in the case of ridge regression, right, even though it tries to reduce the weight values, most of the values will be non-zero. So it could be something like 0.001, or let's say it could even be something 0.025, something like that. Okay, so it will be close to zero, but still it will be non-zero. So you cannot ignore those features as such, because it still has some small contribution to the model. But in the case of lasso, it tries to find a set of weights such that most of them are almost zero. Okay, so if the weights of some features are almost zero, right? So our model is like this, right? Y cap is equal to W0 plus W1 x1 plus W2 x2 plus W dxt. Now, if W2 is almost zero, then we can remove x2 as such from our model, right? It does not make a difference. Almost zero means it will be like 0.0000, like e raised to minus, it will be something like that. So, I mean, so you will think like 0.05 is also like close to zero, but still, again, it depends on the range of the features, right? But if you look at e raised to minus 17 or e raised to minus 15, it's like very close to zero. So then you can comfortably ignore those features, right? So that is why lasso enforces sparsity on the learned weight. So sparsity means we say that a vector is sparse when there are a lot of zeros, right? So the good thing about learning a sparse weight vector is that we can remove all the features that correspond to those zero weights from our model, right? And now that is a good thing, right? So we are doing a kind of feature selection in this manner. We just have to keep the features with non-zero weights. So see how the model is kind of automatically doing feature selection here. Okay, so that is the advantage of lasso, but there is also some disadvantage in that lasso does not perform well when there is multicollinearity and all. So, but yeah, this is one good thing about lasso, and that it helps you to do feature selection. Now, why exactly is it that lasso, tries to give a sparse vector and all? It has to do with the, so it depends, I mean, it has to do with the norm of the vector. So here we are taking the L1 norm, right? So in case of Ritz, we were taking the L2 norm. So I'll share you a resource, I mean, a video in which, they try to kind of explain why this is happening, how the shape of the function changes and also if you are interested, if you want to know more about why exactly this is happening, you can always check it out. I'll add it in the classroom. Okay. Fine. So we look at an example here. So now for the same data set, you can see how ridge and lasso performs. So on top, you can see ridge regression, right? So the model learned in the two cases is kind of similar, but look at the weights. Okay. So here you can see that, so even here, let's say, except till here, the weights appear to be significant. But in the case of lasso, maybe, only so many weights seem to be important. Right. So that is how lasso helps you to perform feature selection. So that means that, these many features. So again, just to help you in interpreting this plot. So the x-axis represents the weight coefficients, right? So this could be the first bar could correspond to W0. The second bar could correspond to W1, something like that. Okay. So similarly here. So these features need not be the, so this could not, I mean, this could be something like W4 also. Okay. I mean, what I'm saying is that the x-axis, the order in which the weights have been represented need not be the same here. Okay. But what is important is that you can see so many weights going to 0 because of which the corresponding features could be discarded. Whereas in the case of grids, that is not happening because of which we'll have to still maintain the entire feature set. Okay. So I hope the distinction is clear. Okay. So then now we have elastic net, which actually is a combination of ridge and lasso. Okay. So that means we are including both the complexity or both the penalty, L1 penalty as well as the L2 penalty in elastic net. So it tries to actually overcome some of the disadvantages of ridge and lasso. Okay. So then elastic net actually helps you to shrink the coefficients as well as it tries to eliminate some of the insignificant ones. Okay. So that was all about regularization. So I hope whatever has been discussed so far is clear with everyone. I mean, I've tried my best to explain things, but still, if you feel that some point is not clear, you guys can please ask. I mean, at least put something in the chat box. I'll just explain it again before we proceed to our next topic, that is logistic regression. So I hope you have understood how by shrinking the weight coefficient, the model complexity actually decreases. So again, I'll share some good resources, right, where they very well demonstrate what exactly is happening. So when you actually reduce the weight coefficients, what happens is that you are suppressing the impact or suppressing the effect of that feature on the model, right? So that means you are trying to avoid too many features, the effect of too many features coming together. So when you try to suppress the weight vector, what happens is that the model complexity decreases in a way that you don't have a lot of things coming in to build a complicated model in your case. So nobody is asking anything, so I hope so much is clear. Then maybe we'll proceed to logistic regression. Okay, so till now we were working with target variable where the y value takes value element of r. Okay. Now coming to logistic regression, our y value will take values in 0, 1. That is, it will take either a value of 0 or 1. Okay. So that means our dependent variable now takes binary values, like for example, yes or no, 0, 1, etc. Okay. So logistic regression is basically a simple algorithm that performs very well on a wide range of problems. So when we have just two values, right, that is something related to classification. We've already seen the difference between regression and classification. So logistic regression is a kind of popular classification algorithm, and it has performed well on a wide variety of tasks. So we'll try to motivate through an example. So consider the task of predicting a person's gender based on their weight and height. Okay, so the gender is the dependent variable and weight and height are the independent variables. Okay, I hope so much is clear. So here we have a data set. I think it's not very clear, but what we have is actually many observations, right? So each row corresponds to one observation. So the first row is, the first element in each row corresponds to the height, and then a comma followed by the weight, followed by a 1 or a 0. Okay, so 1 represents that this person is a male, and 0 represents that this person is a female. This is how our data set looks like. So we have multiple rows. Okay, so each row corresponds to one person. And like that, we have observations or we have details related to multiple people. Okay, so this is how a scatter plot will look like. Okay, so this same data set, if we produce a scatter plot and if we color the data points based on whether the person is a male or a female, this is how it looks like. So we can see that there is no clear-cut separation, right? I mean, that is how it always comes. More or less, that is how it happens in real life also. There is no clear-cut separator as such. So here you can also see a decision boundary, right? So how are we going to come up with a decision boundary with logistic regression? We'll see in a short while. But you can see that there is a decision boundary. So what can be, so suppose that this is how the model looks like, or this is the decision boundary associated with some model, then what you can say is like, okay, if the observation lies above this line, then we can say that it is male. And if the observation lies below this line, it could be a female. But then you can see that there are, okay, I don't know how clear it is, but you can see that there are some blue dots below the line. And you can also see that there are these rose colored points above the line as well. So those are the misclassified points, right? So our model will say that they are, so for example, for the blue colored points below the line, our model will say that, okay, they are female, whereas actually they belong to the class male. Okay, so now we'll see how we can learn such a decision boundary. And then again, we have to come up with a good performance measure, right? So in the case of linear regression, we came up with the least square loss function, right? The squared error loss function, with respect to which we came up with the weight vector that minimizes the loss function. So similarly, here also we have to come up with a good loss function. First, we'll define what is the loss function, and then again we look at how can we, how can we come up with the model parameters that minimizes the defined loss function. Okay, so I hope the motivation part is clear. Exactly like how what the setup is like, I hope is clear to you guys. Okay, so now again we have the binary dependent variable y, and we have these independent variables x1 to xd. So now the logistic regression model is defined as, okay, g of w0 plus w1x plus up to wdxd. So this part I hope it's kind of very much familiar to you from the linear regression part, right? So this, if we use the vector representation, we can write w transpose x. Now what is this g function doing? So first of all, what is this g function? G of z equal to 1 by 1 plus e to the power minus z. Okay. So now why is this G function needed? So first question is like, can we use linear regression model for this problem scenario? That is the first question. Why can't we use linear regression model itself? That is, why cannot we do something like y equal to w0 plus w1x plus w dxt? I want an answer for this question. Why do you think we cannot use a linear regression model in this setting where y is, a binary variable?
Because the answer of y has to be either one or the other, and in a linear regression, you get a continuous value. It's different values.
Right. So here this, thanks, Rafael. So here this will belong to R, right? Whereas in our case, it's either 0 or 1. So how can we, kind of map, or how can we squash these values to 0 to 1? That is what this function is doing, G function. Okay. So this G function is actually trying to squash these values between G. Okay. It is not trying to map values to exactly 0 or 1. It is actually trying to get, okay. So let's say, okay, we'll look here. We have G of Z equal to 1 plus e raised to minus Z. Okay. Now this Z can take values belonging to minus infinity to infinity. Okay. So the domain is the set of real numbers. Okay. I hope the domain, right? Domain of a function. The domain of a function is basically the set of values that can be given as an input to the function. Right. Now, what is the range of values of G of Z? So if we substitute Z equal to minus infinity, right? So then it will become e to the power minus of minus infinity. So then what happens? Minus of minus infinity means e raised to infinity. E raised to infinity is a very large number. So 1 by e raised to infinity will be 0. Right. Then what happens when Z is infinity? Then we'll have e to the power minus infinity, which is a very small value. So then this will be approximately 1 by 1 plus 0, which is 1. Right. So that means what this function does is it takes a value in this range and it squashes these values to this range, 0 to 1. Now, how does that help us? We'll see in detail right now. Okay, but remember that our y still takes value which is either 0 or 1. Okay, it will not take an intermediary value. Okay. So this G function is called the logistic or the sigmoid function. That is why we have this name, logistic regression model. Okay, so now if you substitute this part, right, we have y equal to h of wx given by 1 by 1 plus e to the power minus w transpose x. So this is basically w transpose x, right? So g of w transpose x means instead of z, we can substitute w transpose x. So this is our model. Okay. Now what does this hwx represent? We'll see now. So before that, this is how the logistic function looks like. Okay, so like I said, it takes values from, the range is from minus infinity to infinity. But you can see that the range, right? The range of values taken by g of z is between 0 to 1. So when does g of z becomes 0? When? So, okay, so we have g of z equal to 1 by 1 plus e raised to minus z. So what happens when z equal to 0? When z equal to 0, we have 1 plus e raised to minus 0, which is equal to 1 by e raised to minus 0 is 1, right? So we have 1 by 2. So when z equal to 0, g of z becomes 0.5. Okay, now we'll see how everything fits together very soon. So before that, like I said, logistic regression, as you can see, is an S-shaped function, and it basically squashes the value of z. into the range 0 to 1. So why is this squashing required? I guess is clear to all of you, right? Because if you take W transpose X as in the case of a linear regression model, then we get a range of values, right? There is no restriction or there's no discrete values that we would get in that case. We'll get a continuous range of values. But here our scenario is different in that our Y only takes 2 values. So we somehow have to map or squash these values into either a 0 or 1 value. For that, this logistic function will help us. Okay, so what is the significance of squashing it to this range? Now, HW of X can be interpreted as a probability value, right? So we know that probability of an event lies between 0 to 1. So now that we are squashing it to a value between 0 to 1, now we can interpret it as a probability. Now, what probability? So the probability of Y equal to 1 given X. Okay, so given an observation X, what is the probability that its label or its class is 1? That probability is given by HW comma X. That is 1 by 1 plus e to the power minus W transpose X. Okay, so we learned a model such that this quantity here will give us the probability that the class of this corresponding X is 1. Okay, so that is how the model is going to be learned. So then what is the probability that Y equal to 0 given the same observation X? Somebody should answer. Other than Raphael, probably somebody else. Anybody else could answer? So this is the probability that Y equal to 1, right? So Y can take only 2 values, 0 or 1. So if this is the probability that Y equal to 1, then what is the probability that Y equal to 0? Fast, we are already running out of time. Same probability, no, it's 1 minus that, right? 1 minus H of Wx, right? So if the probability that Y equal to 1 is 0.4, then the probability that Y equal to 0 will be 0.6, right? Because either it will be 0 or 1, right? So I hope everybody got that point. So just simple probability, right? Because it can only take 2 values. We know that if this is the probability that Y equal to 1, then this is the probability that Y equal to 0 is given by 1 minus HWX. Okay. So now comes the importance of the other part. Okay. So now we get these probabilities, right? So our model will predict some value between 0 to 1. But our Y is either 0 or 1. Right. So how to map these probability values to 0, 1? So how to map a value between 0 to 1 to a target value which takes either 0 or 1? We'll put a threshold. We'll say that, okay, if the H of HWX is greater than 0.5, then we'll say that Y equal to 1. Okay. If it is less than 0.5, we'll say that Y equal to 0. That is kind of a most straightforward approach, right? Most simple approach. So our model will calculate the HWX, which is the probability. And if HWX is greater than 0.5, it will say that it belongs to class 1, otherwise it belongs to class 0. Now, when is HWX? So HWX, if you remember, is G of W transpose X. Right. So HWX greater than 0.5, or let's take the case, when does HWX equal to 0.5? We already saw, right, in this function, when W transpose X is 0. Right. So HWX is basically G of W transpose X. So G of W transpose X becomes 0.5 when this value becomes 0. So you can consider Z equal to W transpose X. So the question is basically, when does G of Z becomes 0? Sorry, when does G of Z becomes 0.5? When Z equal to 0. Right? So Z means W transpose X equal to 0. So that gives us the decision boundary. Okay. So this happens when W transpose X is greater than 0. So you can see from this figure, right? See, when W transpose X is greater than 0, then we have these values. So if you look at here, right? So for all these values, G of Z is greater than 0.5. Right. So that means the decision boundary is given by W0 plus sigma Wixi equal to 0. Okay. So is this clear? How the decision boundary is obtained? Do I need to explain something again, or you are getting the idea what is happening? Nobody's replying, but so I hope so. I hope you guys are are able to follow whatever I'm saying. So now again, you can see that now the decision boundary is linear. Okay, thanks, Ashwini. So again, we can see that even though we are using a non-linear function G, okay, we are getting a linear decision boundary, right? So that is quite interesting because people tend to think that, okay, we are using a non-linear function, so the decision boundary would be non-linear. No, the decision boundary is linear in terms of the weights and these features exist. Okay. So can I take 10 more minutes? Would that be okay? I thought I'll finish with logistic regression. Ashwati, can I?
Yeah, ma'am, sure.
Okay, thanks. So now we look at the cost function, right? That is the important part. So now we have seen what our model is going to predict. So we saw that it is going to predict some value between 0 to 1, which is actually interpreted as the probability that the observation belongs to class 1. So that is a summary of whatever we have seen till now. And now let's see how the cost function is defined. So we have to find a weight vector W such that this probability value, right? That is HW of X is large when X belongs to the class 1. Right. So if X actually belongs to class 1, then we want this value to be large. And it should be small when X belongs to class 0. Right. So when X belongs to class 0, this should be small. Or in other words, probability that Y equal to 0 given X should be high. So that is our goal. Okay. So for that, we used a cross entropy loss function. Okay. Now, on a first look, it seems complex. Lot of terms, summation, y, then we have log, everything. But now let's look at it in detail and we'll see that it's very simple. Okay. So now note that, okay, this summation, if you remember, is because we are summing the loss for all the data points, right? But now if you look at whatever is there in this expression, we see that there is a yi and there is a 1 minus yi term. Now remember that yi can be either 0 or 1. So when yi is 0, what happens is this term disappears, right? We are doing a product 0 into something. No, it disappears. We have only this 1 minus 0 term here. Okay, so this will be 1. 1 minus 0 will be 1. What is this? Here what we are looking is log of 1 minus h of w comma xi. So if you remember, this is the probability that y equal to 1 given x. So what is 1 minus probability of y equal to 1 given x? Probability that y equal to 0 given x, right? So what we are doing here is log of probability of y equal to 0 given x. So if this value, that is probability of y equal to 0 given x is 1, let's say. What is log of 1? What is log of 1? At least answer that. What is log of 1? Somebody?
0.
0. Thank you. 0. So this will be 0. Log of 1 will be 0. That is, the error is 0. Why? Because we have correctly predicted, right? It belongs to class 0, and we are saying that the probability that it belongs to class 0 is 1. Very nice. Now, what happens if this is 0? That is the probability that y equal to 0 given x is 0. What is log of 0? What is log of 0?
Infinity.
No. Log of 0 is minus infinity, right? See, 2 raised to, if we are taking 2 raised to minus infinity, that is 0, right? So we say that log of 0 to the base 2 is minus infinity. Same with e, I mean, whatever base we are taking, it's the same, right? So we have minus infinity, but then we have a minus here. So that means this loss will become plus infinity. Now see, so if the class is if the actual class is 0, and we are saying that the probability, or if the model is saying that the probability that y equal to 0 is very small, that is close to 0, then the loss that is being incurred is very high, right? So now you can see, right, how the penalty is coming in. Now similarly, you can see what happens when ya equal to 1. So when ya equal to 1, then this term will go. Then what is important is this part, right? We have log HW xi. So if this HW xi, if you remember, is the probability that y equal to 1 given x. So if this value is 1, then again our loss will be 0. And if this is 0, then our loss will go to infinity. So I hope now you are getting how the cross entropy function is kind of working, how the penalty is happening with cross entropy loss function. So it's very similar. It's just that it is combining two things together. And what is to be noted is that only one term will be non-zero for each xi, depending on the value of ya. Okay, so how can we minimize the loss function? So minimizing this loss function means that HW comma xi should be large when ya equal to 1. True, right? So when ya equal to 1, when the actual class is 1, then we should get this probability value to be high. And on the other hand, we should want to have 1 minus HW to be large, or 1 minus HW to be large means HW should be small when ya equal to 0. So always remember that HW is the probability that y equal to 1 given x. So when y equal to 0, the probability that y equal to 1, the probability that the model says that y equal to 1 given x should be very less, right? If it is actually belong to class 0, our model should not say that, okay, there is a good probability that it is belonging to class 1, right? And another thing to note is that this function is convex. Okay, so it's not very straightforward, but it can be proved that this function is convex, which makes it convenient for us to use gradient descent, right? So we don't have to worry about the local minima and all. We can always be, it is always guaranteed that gradient descent will give us the minima. Okay, so that is another good thing about the cross entropy function. Okay, so if you read about logistic regression, in some resources, in some literature, you will see that instead of the cross entropy function, they'll talk about maximizing the log likelihood function. Okay, so I just wanted to discuss about that. I just wanted to mention about that because I don't want you to get confused, because okay, you will be suddenly thinking, where did the cross entropy go, and from where did this log likelihood maximization come into picture. So basically, if you look at this carefully, you can see that this thing is actually equivalent to minus L of W. Okay. So that means when we are trying to minimize the cross entropy, right? So if when LW decreases, minus LW will increase, right? So suppose we have Z. So when Z increases, minus Z will decrease, right? So same thing is happening here. Because, so if you want, okay, I don't think I have time, but if you expand this, right? So there is a log product and all. So you know that you just have to apply the logarithm rules, you know, right? Log AB is equal to log A plus log B. So then if we apply that rule, what happens is this summation will come outside. Okay, then we have these two terms here, right? Then again, we apply the same rule. Then what happens? And we'll get log HWXIYI plus log this term. Then we know that log A to the bar B is basically B log A. So then we'll get the same expression without this minus. So that is why I'm saying that this is actually equivalent to negative cross entropy. So when you try to minimize the cross entropy, you are basically maximizing this function, cross log likelihood function. So, so from the probability point of view, right, you can actually motivate how your how the log likelihood function is all coming into picture. But then I thought many people would not be that comfortable with probability and all. So that is why I went with the cross entropy point of view. But anyways, whatever is happening is just the same. It is just that we are looking at it from 2 points of view. That's all. Okay. So I hope the cross entropy part is clear. So just to illustrate, this is how the cost function will look like. So when y equal to 1, so look at the blue curve. So when y equal to 1, so this h theta of x is basically our hwx. So I took this figure from somewhere else. So that is why this terminology difference. Okay. So always remember that our hw of x is equal to probability of y equal to 1 given x. Okay. So when y equal to 1, if hwx is 0, so see that the cost is very high. But then as this value increases, this curve comes down, and finally when hwx is 1, we have a loss of 0. Similarly, what happens here for the case when y equal to 0? When y equal to 0 and hwx is 0, right? So that means we are saying that the probability that y equal to 1 is 0, which is correct. When the actual target class is 0 itself, right? So then we have a 0 loss. But then as this probability increases, the loss increases, right? So this is how the loss function would look like. So I'll just complete with the problem definition part, and then we look at the gradient descent maybe in the next class. Okay. So so what we have with us is n observations, right? Paired observations. We have xn and the corresponding label yn. Where xn, as we have already seen, is a vector of features, and yn is either 0 or 1. If you remember, for regression, this belongs to R. Whereas now for classification, we will take either 0 or either 1. So I hope you guys are familiar with the difference between the squared brackets and the flowered brackets. So flowered bracket means it will take only one of these values. When we have the squared brackets, it means it will take values given by the range 0 to 1. It will take values between the specified range values. Okay. So now our goal is, okay, we have to predict the y value for a new x value. So for that, what we have to do, we have to estimate the weights, right? We have to estimate the model. So the weights have to be estimated such that we are minimizing the cross entropy loss function. Okay. So this is the cross entropy loss function, and HWXI is basically 1 by 1 plus e raised to minus W transpose xi. Okay, so maybe I'll stop here and I'll continue with the partial derivative and the gradient descent part in the next class. So I hope so much is clear to everybody. If there is any doubt, you guys can always ask me. So if there is some suggestion about improving, then please do mention the same in the quiz. Okay, so I have added a question there. So some students had mentioned about including examples. So I've tried to include examples and figures and all, but otherwise I'm not. I mean, I'm not exactly able to understand what you require. So if you could detail or if you could explain a little bit more as to what exactly would be helpful for you, then I'll try to include that also. Okay.
പഴയ കൂടെ ഒതുക്കിക്കളും കിടന്നവിടെ വണ്ടി വെച്ചിട്ട്
So also everybody should try to do the programming exercises and the quiz also, right? I think for the quiz 3, very few people have attempted. Okay, Ashwati, I think it's okay. Somebody has written. Okay. Okay, so okay, fine. So I hope it's clear. Those concerns are clear to you, Bal Subramaniam. Okay. So if there is something else, you can always let me know. I'll try to include that in the subsequent sessions. So Ashwati, if there is nothing else, then maybe we can stop, right?
Yeah, ma'am. Right.
Okay.
Thank you, ma'am. Thank you for the session. Hello, ma'am.
Hello.
മാമിനാണ് ഇപ്പൊ ഹോസ്റ്റ് പ്രിവിലേജ് ഉള്ളത്. ഞാൻ നേരത്തെ ഒന്ന് ലെഫ്റ്റ് ആയി പോയായിരുന്നു. അപ്പൊ ഹോസ്റ്റ് മാമിന് മാറിയിട്ടുണ്ട്.
എൻഡ് ചെയ്താൽ മതിയല്ലോ അല്ലേ?
അപ്പൊ മീറ്റ് ഒന്ന് എൻഡ് ചെയ്യാൻ.